Welcome back to today's Explainer. In the world of advanced materials, we are always hearing about the latest and greatest iterations of carbon fiber, Kevlar, or graphene, right? But hiding in plain sight, literally operating in some of the most punishing, high-stakes environments on Earth, is this legacy supermaterial that completely redefines our structural limits. I'm talking about boron fiber, and specifically, a strictly non-optical, highly engineered variant that solves complex engineering problems standard composite materials simply can't handle. When we push the boundaries of aerospace or high-performance mechanics, engineers constantly hit these physical thresholds where traditional materials just yield or fail. That is exactly where this specific variant steps in. So today, we're going to unpack its structural anatomy, its specific mechanical advantages, and the incredibly high-stress load paths where this unique material absolutely dominates.
Now, let's get one thing straight right out of the gate. When we hear the word fiber today, our minds naturally default to those optical strands rounding data all over the globe, right? Well, scratch that. We need to separate that entirely from what we're looking at right now. This boron fiber is strictly non-optical. No way around it. It does not transmit light, data, or signals of any kind. Its sole purpose, raw, unyielding structural integrity. It's a load-bearing workhorse, not a conduit. In material science, the naming conventions can kind of be misleading sometimes. While optical glass fibers are engineered for total internal reflection to keep signal loss down, this non-optical boron fiber is built to minimize physical deflection under massive, massive loads. So the focus shifts entirely away from bandwidth and clarity straight into compressive strength and rigid permanence.
So, if it's not made for data transmission, what exactly is it? And how does it pull off this structural superiority? Well, the secret is all in its anatomy. See, this isn't just some pure extruded strand of a single element. No, it's a highly engineered composite. It's basically the deliberate marriage of two vastly different elements, tungsten and boron. And this isn't some random pairing either. It's a highly calculated structural design. The goal is to synthesize the unique properties of a dense, high melting point metal core with this rigid, lightweight metalloid. By combining these two elements, engineers aren't just doing simple addition with their properties. They're creating this amazing synergistic effect. The final composite handles stress profiles that, honestly, neither element could ever survive on its own. Okay, let's break down how that composite actually comes together. The manufacturing process actually doesn't start with boron at all. It kicks off with a microscopic tungsten wire acting as the foundational substrate. You can think of it as the spine of the material. Then, through a really precise chemical vapor deposition process, that incredibly fine tungsten core gets heavily coated with an exterior layer of boron gas, which solidifies right onto the wire. It's a highly, highly intentional microstructure. The tungsten provides the initial tensile baseline and acts as the necessary heating element during deposition. Then the boron jacket comes in and locks the whole thing into this intensely rigid, immovable state. The final result? A monofilament with a massive modulus of elasticity, which fundamentally changes how the strand reacts to physical forces. Now, to truly grasp its value in modern manufacturing, we've got to benchmark it against the reigning champion of the advanced materials world, carbon fiber. We all know carbon fiber is the default ubiquitous go-to for high-end, lightweight manufacturing. It's prized for that exceptional tensile strength-to-weight ratio. So why bother going through this incredibly complex, expensive, and energy-intensive process of coating tungsten wire with vaporized boron? Well, because in highly specific engineering scenarios, carbon fiber actually hits a structural wall. It has a limit. It all comes down to an engineering trade-off. When designers need material properties that push way past the standard performance envelope of traditional carbon composites, they absolutely need a challenger, engineered to surpass those exact limitations. The main differentiator between standard carbon fiber and our tungsten boron composite really boils down to one vital metric: absolute stiffness. Look, while carbon fiber is famous for its immense tensile strength, meaning it strongly resists being pulled apart, it actually can still flex under certain directional forces. Boron fiber, on the other hand, is specifically engineered for unparalleled structural rigidity and exceptional compressive strength. It is literally designed to resist bending, compression, and deformation under immense stress profiles where carbon fiber might just yield, buckle, or introduce unwanted flexibility. When you place a structural component under severe compression, the thicker diameter and the inherent stiffness of the boron monofilament provide a buckling resistance that standard carbon tow simply cannot replicate. Looking straight at the engineering data from our sources, the claim is pretty definitive. It can be even stiffer than carbon fiber. And wow, in the advanced materials sector where carbon fiber is widely accepted as the absolute gold standard for rigidity and lightweight strength, producing a material that actively eclipses its stiffness, that is a profound advantage.
We're talking about a modulus of elasticity that significantly outpaces standard aerospace-grade carbon. When an application demands a near-zero tolerance for flex, boron is the material that provides a structural guarantee that standard composites just completely miss. It isn't just about being strong, you guys. It's about flat-out refusing to change shape, regardless of the external pressures slamming into it.
Okay, so understanding that underlying physics dictates exactly where this material is deployed out in the real world. A material this specialized and, frankly, this expensive and challenging to make is not getting tossed into everyday commercial items. No way. It is strictly reserved for zero-failure environments. When engineers are staring down an intersection of massive compressive forces, extreme aerodynamic loads, and an absolute non-negotiable requirement for structural rigidity, they turn to boron. These are the high-stress load paths where the cost of material failure is, quite simply, catastrophic. The choice to use boron fiber is a highly calculated decision to prioritize unyielding stiffness over almost every other manufacturing variable out there, including cost and ease of fabrication.
And that brings us directly to its high-stakes applications. First up, consider aerospace, specifically the empennage and wingskins of high-performance fighter jets. When you're moving at supersonic speeds, aerodynamic flutter can induce vibrations literally capable of tearing an airframe apart mid-flight. But the unmatched stiffness of boron fiber stops that flex dead in its tracks, totally stabilizing the aircraft's control surfaces. And interestingly enough, you see the exact same physical principle applied in professional sports equipment, like elite golf club shafts. The crazy rigidity minimizes unwanted flex and twisting during the swing. That ensures zero energy is lost, maximizing the kinetic power transfer directly to the ball. So whether you are managing supersonic aerodynamic pressures or the massive high torsion of a pro golf swing, its sheer lack of flex is for sure its absolute greatest asset.
So we've seen how a microscopic tungsten wire, totally jacketed in boron, quietly outperforms carbon fiber in some of the most demanding physical environments we've ever engineered. Honestly, it just goes to show that sometimes the absolute most advanced and capable solutions out there aren't necessarily the most famous ones in the mainstream. As aerospace designs push further and further into hypersonic speeds, and industrial demands for precision and durability just keep increasing, it really begs the question, are we approaching the physical limits of our standard composites? And will legacy, highly specialized materials like boron fiber ultimately become the blueprint for our future high-stress engineering? Definitely something to think about. Thanks so much for joining me on today's Explainer, and I'll catch you next time.